Hello again. So for my second optimization question, I was asked that a rectangle is inscribed inside a semicircle with a radius of 8 units, and I have to find the dimensions that will maximize the area of the rectangle, determine this area, and prove that this is the maximum. So to start with, like the first question, I decided to draw a sketch to represent what was going on in the question and what it was asking. So it's basically saying that there is a semicircle, and inside this semicircle lies a rectangle. We're only given one piece of information, and it's that the semicircle has a radius of 8 centimeters. And then we're asked to find what can the maximum dimensions of this rectangle be to fit inside this semicircle. So to start with, we need to create an equation that represents the area of the rectangle, which in this case is 2x times y. And then after that, we basically want to solve for x and y, but because, pardon me, because there's two different variables on one side, we can't actually solve it. So we need to take one of the unknowns and represent it in accordance with the other unknown. So in this case, I represented y as being 64 minus x squared, the square root of 64 minus x squared. And I found this by basically using the equation of a circle and then plugging in the 8 that we know into the r and basically solving for what y would be. And then representing y in terms of x instead of it just being y on its, by itself. That way we can now solve for the variables. So this is the final equation that I had, that I represented the area of the rectangle with. And after that, we needed to find the first derivative. So to find the first derivative, I simply used the product rule, and then I ended off with this line over here. And then after we find the first derivative, we actually want to find the roots of the first derivative. Now, the reason we're finding the roots of the first derivative is because the roots of the first derivative represent either the maximum or the minimum on the original function. So to start off, I wanted to find what makes this part of the function 0, first of all. And I realized that it's actually undefinable because since it's to the power of negative 1/2, when we simplify it, the derivative of this section will actually just be undefinable. Or sorry, there is no 0 on this part of the equation. So I moved on to this part of the equation, which is 64 minus 2x squared, and I found that for it to be 0, the x is going to have to be the square root of 32. So after we found the x, I basically plugged the x into the original circle equation over here to find the y. And then basically I solved for the y, and now we have the maximum x and the maximum y. The reason we have the maximum x is, as I said before, since this is the first derivative, finding the root of the first derivative gives us either the max or the min of on the original function. And since in this case we're told that there will be a maximum, we know that this is a max. And then we plug in to find the maximum y, which is why the y as well is maximum, because we use the maximum x to find it. Said maximum a lot of times. Anyways, after we found the x and the y, we need to plug them back into the original equation that represents the maximum area of the rectangle. So we get, after we put in the x and the y, we get a total of 63.3 units squared. We were not given an actual measurement, so if it was meters, this would be meters instead of just units. So to finalize the dimensions, if the dimensions were to be the square root of 32, which is approximately 5.6 units by 5.6 units, this will result in the maximum area possible for the rectangle to be inside the semicircle. Now, to prove this, we can use a simple interval chart. So we know that the x-intercept is at the square root of 32, which is approximately 5.6. So we basically want to input values that are less than the x-intercept, as well as values that are more than the x-intercept into the first derivative. And then if the answer is a positive, then we can assume that on the original function, that interval is an increasing interval. And then we can assume if it's a negative on that interval, on the original function, it will be a decreasing interval. And as we can see here, it goes from increasing to decreasing, and we all know that if something goes from increasing to decreasing, it actually creates a maximum. And that's how we know for sure that this answer is the maximum dimensions possible for the rectangle. And yeah, that is the final answer, and these are the final dimensions needed to get the maximum rectangle inside. the semicircle. Thank you so much.